Hey guys, welcome to another video. Today's lesson comes from the Extension 1 syllabus. Now, I've had a few requests for this topic, so I'm quite excited to give it to you today. So the topic is binomial probability, and the specific area of concern is sample proportions. Now, I think it's fair to say sample proportions is probably it's not very clear in a lot of students' mind of what's the difference between binomial probability in itself and sample proportion. So today's lesson hopefully helps you set aside the differences, right? Or see the differences side by side, and then appreciate that some questions you can actually do use both methods, right? To do the best question that I have for you to illustrate that is a question from the HSC 2022, which I'll go through today. Now, before I go on, if you haven't already done so, please like the video, subscribe to the channel, tell your friends. And if you're studying for exams, we at nexteducation.com.au, we have past papers that we have for our students that are available to you for free. Download them, do them, and if you need the solutions, just email us at info@nexteducation.com.au, and we'll send you the solutions, guys. Let's dive right in. So, for those that haven't already done so, please look at. Make sure you watch the videos that I've already done on binomial probability, just to get the framework for how binomial probability works. Because for this video, I'm just going to dive right in and do binomial probability with normal approximation as a starting point. So let's get started. So now, binomial probability. Oops. Yeah. Sample proportions. Now, the best way for me to sort of illustrate differences is, let's start with an example, right? Let's go a multiple choice question, an MCQ, so test, right, has n questions, right? Where probability P equals to, also width, maybe width is a better word, yeah. Width probability P of randomly getting a question correct. So this just defines an example that is a binomial distribution where there's like n questions, and let's say, for example, with each question there's 4 choices, and if there's 4 choices, if I was to randomly select one, that's a quarter. That's what P is. P is the probability that if you randomly selected a question, a solution for one question, what's the probability you're getting right? So if there were 5 choices, P would be 1 on 5, right? So basically, probability P, and n is like the number of trials, right? Okay, now, if this was the case, right, I want you now to sort of see, I'll illustrate 2 cases, right? So if we just did binomial probability, yeah, with using normal approximation. Now, for those who have seen the video that I did on this, the diagram that I really like to draw, right, and I think it's really, I think it's a really nice way of summarizing everything, right, is this. So if I had, let's define X, and that's actually, for this video, it's really important for you to define what X is. So go let X equal to the number of correct solutions, right, in this specific example, right? Yeah, because later for sample proportions, I'm going to define a new variable that represents something similar, but a little bit different. Now, if X is the number of correct solutions, then I know, right, then X is a binomial variable with parameters n and p, right? Yeah, in fact, what I'll do, I'll label that, move it down. Let's just call this binomial. Right? So binomial, X is binomial variable, n and p. Now, I need to move that onto normal distribution. And guys, what's important is for normal distribution, the reason why it's mathematically easier to do is because it's a continuous random variable, right? More things are open to us when it's binomial. It's a lot of manual discrete calculations, but when it's continuous, we can use integration, right? In universities, that's what they do. But in the 3-unit course, we basically use the table of values, right? So with the normal distribution, what we want to do is basically redefine x as a normal distribution with mu and sigma squared as our parameters, right? Mean and variance. Now, with that in mind, right, how do we get from binomial to normal? We basically let or derive mu as NP, right? That's expected value, and sigma squared as P1 minus P, right? Yeah, that's the converter, right? So if we express this, right, we go up here. Now, there are cases where normal is not very appropriate to use as an approximation for binomial. In those cases, generally speaking, n is really small. So if there's a small sample, the normal approximation isn't great. So for example, if it's a multiple choice with 10 questions, you probably shouldn't use normal approximation. But if it was a multiple choice exam with 100, 1,000 questions, then yes, right? Using a normal approximation is usually the way to go. The normal rule of thumb, do you guys remember from the last video, n times p, if that's greater than 5, and n times 1 minus p, if that's greater than 5, then it's appropriate, right? But guys, once we go normal, right, yeah, we then need to, now we can't really do anything with that in the 3-unit syllabus. We then need to go further and go standard normal, right? Yeah, so we go from the variable of x, we go and convert that to z, which is standard normal, where the mean is 1, sigma squared is, sorry, mean is 0, sigma squared is 1, right? And the way we do that is basically we standardize by going let z equal to x minus mu over sigma. And that's important. Now, especially important when we talk about sample proportions in a few minutes time, right? So once we do that, guys, what we can do then is basically use table of values to do it. Now, I like this. I like this sort of diagram because it is exactly the sort of flow chart of things that I need to do, right? I start with binomial, right? I convert that using mean and variance formulae to normal. And then once I go normal, I convert that to standard normal by standardizing, right? With that z-score formula downstairs. Now, if this is binomial probability over to the right, I'm going to do an equivalent, right? So standard proportion, sample proportions. Now, what is it? What is the difference and how do we know, right? So sample proportions is very similar in that instead of letting x be the variable, we'll let p hat be the variable, right? And instead of saying, now x is the number of correct solutions, p hat would be the proportion, right? Or percentage of correct solutions. Now, it's very different, right? So for example, questions about, I'll give you an illustrative example, right? Let's say, for example, there are, now I'll rub this off in a sec, right? But let's say there are 20 questions, 20 multiple choice questions, right? What's the probability of at least 2 correct, right? If that was the question, right? If I was to do it under binomial probability, I would define probability that x is, what's that, greater than 1, right? At least 2 greater than 1, right? That's how I would do it. If I was doing under sample proportions, I want the proportion, right? So basically, probability that p is greater than, now what percentage is that? 2 correct is 10%. So probability that the proportion is greater than 10%. That's the difference. So mathematically, it's the same thing. One says I want greater than 1 correct, which is 2 or more, right? The other one says, because I want 2 or more, that's like 10%. So I want my probability to be greater, my proportion to be greater than 10%. Now, if you did all that, mathematically it should be the same. Now, let's actually look at, in terms of formulae, how that looks like under both. So this is what I'm going to do. Right, I am going to think. Oh, before I do that, actually, let's be very clear when I set it side by side. Right, what the formula is for p hat. Right, so p hat is ultimately x divided by the total number of questions in this case, right? And in this case, it's really important for you to identify that, right? And I'll sort of zoom out to sort of illustrate that to you. X is the variable, right, that I started with over here. It's the same variable. So when I do expected value, when I do mu and sigma squared, it's the same for that X. Now, and then it's really important for you to identify that this over here, the n over here, that's constant. Yeah, that's constant. So when I transform variance later, that constant there is important. Now, what I'm going to do then is I'm going to get the same sort of diagram here, and I'll show you the only points of difference, right? The only point of difference is this bit here, right? When you do sample proportions. Sample proportions, we're going to basically replace that middle section with the formulae relating to sample proportions, right? And I'll show you how I'm going to do it. So I'm going to remove that, remove these, remove these. Might need a bigger box there, actually. So maybe I'll just remove the box. Yep. And gently remove this. Okay. I'll remove this as well. I'll just remove that. Yep. All right, cool. Now, so first thing I'm going to do is replace the normal expression to be p hat, right? That's the variable that I want to define, and that's normally distributed. Now, but the parameters in normal, I'm going to put mu with a p and sigma squared with a p. Let me get rid of this side. Yeah, sigma squared with a p. So, because with p hat, there's a new mu and a new sigma squared, right? What are they? So this is how I want you to derive it. Close. So with the mu, now I know it's going to be, right, because the variable p hat equals to x on n, right? The expected value of x is np, right? And I now need to divide it by n, so it's just p. So whenever you see expected value of p hat is p, right, mathematically, that's why it's true. Now, sigma squared, right? Normally, the variance, now, when I do variance, I'll actually, do you guys know, right, just to make sure, right, the variance, if I ever have a constant, let's say 5 of x, right? If I was to transform this and take the 5 outside of the variance, right? Yeah, hopefully you guys know, hopefully your teachers have told you this at school, that when you take it out, it's squared. Right? It's not 5, the transformation is a squared transformation, right? So whenever you take constants out, it's squared. The reason why I say that is because if I take variance of the blue on the pink, right, I don't just get like I don't get the variance which is np 1 minus p on n, right? It's n squared, right? That pink square there becomes square. So that pink n there becomes squared, and so then my things cancel out, and you get p 1 minus p on n. Yeah, that becomes your mu. Yeah, your mu and your sigma squared, right? So I got new formulae to plug into these two, right? So actually, while I'm doing that, I'll put a little p down here to signify that they're not the original, they're transformed. And once I do that, then the z score, right, is exactly the same. It's x minus mu on sigma, but the only difference is that that's p and that's p. Yeah. So whenever you see this, by the way, right, sometimes you might see the formulas in textbooks, right? Say that is sigma, right, equals to square root of p 1 minus p on n. Yeah. While over here, you might get sigma equals to square root of n p 1 minus p. Yeah, that's sigma. Both of those are the same, right? Both of those are the same mathematically. They will get you to the same answer. Now, just to demonstrate that, right? Let's do HSC 2022. So, but I guess what I'm trying to get to is whenever people look at the formula and they're like, I'm confused. Why are the formula different? It's because the variables are different. That's X and that's P hat, which is X on N. That on N gives you different expressions for mu and sigma squared when you try to standardize. But the process between the two, right? The only difference is the middle part, right? The only difference is the middle part because the other parts, that's binomial, and this standard normal, they're exactly the same. We just need to get there. The journey is a bit different, right? Let's talk about that in context of the HSC question that I'm going to do now. All right, let's go through this, right? HSC 22. So with this question, right, you can sort of see when it starts off, right, a chocolate factory sells 150-gram chocolate bars. Now, I'm just going to say it now. That 150 grams, that number of 150, nothing to do with anything. It's just a bit of a distraction, right? So 150 grams, okay. There has been a complaint that the bars actually will weigh less than 150. So a team of inspectors was sent to the factory to check. They randomly select 16 bars. Now, why is that important? Because that's N, right? That's N. Weighed them and noted that 8 bars, right? 8 bars weighed less than that, okay? Maybe that's important, but we'll see. The factory manager claims that 80% of the chocolate bars produced weigh 150 grams or more. Now, that's important, right? 80% weighed that, right? Yeah, so that actually tells me, on average, 80% weighs more, right? Now, I'll get there in a sec why that's important. So let's look at the question. The inspectors use normal distribution, right? To the binomial distribution to calculate the probability of P. Now, P is the probability of having at least 8 bars less than 150 grams, right? In a random sample of 16. Okay, calculate P. Okay. Now, I won't do question 2 yet. Question 2 is really easy, but for now, part 1, right? Let's illustrate this, right? You know what? To do this question, I'm going to do something that is quite powerful. I'm going to do it by binomial probability, and then I'll do it by sample proportions, right? And illustrate that both answers are the same. Just the way you approach it is different. So maybe I'll go number 1. Let's just use normal binomial probability. All right. So where you let X equal to now, having at least, okay, so number of bars less, yeah, less than 150 grams, right? So in this question, they're basically saying, right, they've defined P to be at least 8 bars weighing more. So 8 weighing less, right? So if X is weighing less, I want at least 8 weighing less. So basically I want P of X at least 8, so greater than or equal to 8. Okay, just because now I think there's a bit of a confusion point where it says the words less than 150. Less than 150 now is just my variable, but I want at least 8 of them, right? So that's actually what I want. Now, just like before, I now have a normal, right, expression. I want to standardize that. What do I need for standardizing, right? Remember, I need to get from that to something that looks like Z, right? What do I need? I need Z X minus mu on sigma, right? I need mu on sigma. Yeah, so off to the side, right? I'm going to define them, right? So off to the side here, I know that X is, right, a binomial expression with N and P. Right, I know that. Now, in this question, what is N and what is P, right? I know that N is 16, right? Because there's 16 bars that we're looking at. Now, what's P? Let's go back over here to this blue point here. The factory manager claims that 80% of the bars are more than 150, right? Are more, yeah? 80% of them. So that means the probability, right, of me getting, so this is on average. So the probability of me getting less, right, than 150 would be 0.2. Does that make sense? Because he claims that on average, 80% of them are more, I'm defining x to be less, so then I want the opposite of that. So in this case, p is 0.2. Now with that, I can derive what mu is, because I know that mu is equal to np, right? 16 times 0.2, which is 3.2 on your calculator. And I know that sigma squared is equal to n times p times 1 minus p. That's 16 times 0.2 times 0.8. And on your calculator, that's 2.56. Now, and if you square root of that, it's actually quite a nice number, 1.6. All right, I now have all the ingredients I need to standardize. So let's standardize, right? So I know that to standardize, I take the original x value of 8 minus mu divided by sigma, right? And if you did that, right, you sort of get like z, I believe that's 3. Yeah, do it on your calculator. I think it is. Now, once you get that, guys, you basically have in 3 in maths, they'll give you the broad table, right? They give you the broad table with numbers such as this one, right? And you just got to find. Now, but before I do that, to do greater than, it's 1 minus probability of less than. Now, in this case, right, the equal sign really is irrelevant. Technically speaking, right, I should have done greater than only, but because less than equal to is what the table tells you. But anyway, in this question and in just maths in general, in 3 to maths, greater than equal, less than equal, same thing, right? You don't need to worry about the overlap in the equal sign. Now, less than equal to 3. Let's go to the table. Where's that? That is here, 0.9987. So 1 minus 0.9987. And if you punch it in the calculator, 0.0013, and that's the answer. Guys, that's how you would do this question using binomial probability. Now, by the same token, let's do exactly the same question, but using sample proportions, right? So I am going to, got a slide prepared, I'm gonna, oops, sneakily on this side, do exactly the same. And I'm just gonna show you, right, how I'm gonna edit it, right? So obviously, right? So with top 2, sample proportions. Now, if x is defined as a number, right, we're going to define a new variable, right? So I'll just move this slightly down. All right. I'm going to define a new variable, p hat, which is the proportion of bars less than 150 grams. And just to be absolutely clear, right, p hat equals to x divided by n, right? Yeah, x divided by n, yeah, which is 16 in this case. Now, so when I do my probability then, right, it used to be find the probability that I want greater than 8 out of 16, which is half, right? So I want the probability that the proportion of bars is greater than 0.5. Does that make sense? Because 8 out of 16 proportionally is 0.5. Now, and with that in mind, right, I'm going to need a mu p over here, right, to standardize it. So I'm just going to remove everything that I don't need, right? I don't need this. Right? Don't need that. Right? Everything else actually is fine. No, so now over this side, right, that's still true, right? That's still fine. But these guys here, yeah, they're going to all change. I'm just going to delete this. Yeah, just delete that. Now, and let's put in new ones. So for p hat, right, for p hat, I know that mu p is going to be just p, right, 0.2. And I know that sigma p is going to be square root of p 1 minus p on n from the previous page. That's like square root of 0.2 times 0.8 on 16. If you punch in the calculator, I believe it's quite nice actually. 0.1. Nice. Yeah. Then now that you've got those numbers, for my standardization step, right? That's the only thing that's different here. Would be 0.5 minus 0.2 minus mu over sigma 0.1. And if you punch it in the calculator, it's 3. Surprise, surprise, it's 3, and then you use a table and you get the same answer. Guys, so what am I trying to say? The only point of difference is that we defined a new variable p, which is a proportion of bars less, which is x on n. And when we talk about proportions, then the probability is expressed as a percentage, right? And by that, I mean, it used to be 8 bars out of the 16. Now we're going, find the probability that the proportion is greater than half, because 8 on 16 is half. And then you use this bit here, right? Is a little bit different. So mu is different, sigma is different. But then when you plug it in, by the time it goes into your calculation to standardize, it goes back to 3. And then you use a table, you get the same answer. So what am I trying to say? Sample proportions binomial theorem, exactly the same outcome. Now, and then very quickly, just for completeness, let's calculate, or let's finish up the question part 2. Factory manager disagrees with the method used by, now the method in this case is the normal approximation, right? Described in part 1. Explain why the method might not be valid. Now, when does a normal approximation, when's that inappropriate? When the numbers are too low. How do you know it's too low? So they basically use rule of thumb. If n times p is greater than 5 and n1 minus p is greater than 5, then it's appropriate. In this case, right, n times p is equal to 16 times 0.2, which we know that's the same as mu, 3.2. That's less than 5. So therefore, right, method may not be valid because the sample is too low or small. Yeah, that's really the reason, guys. And that's it. So the difference between binomial probability and sample proportions is merely the way that you define the variable that you're looking at. If you're defining it as a proportion or a percentage, sample proportions. If you're defining it as the number of countable items, in this case, 8 chocolate bars, is a countable item, then that is binomial probability. And once you define your variable, use the mu and sigma squared or sigma to get you to your z-score. Once you get your z-score, use the table to finish off the question. Guys, hopefully that was illustrated for you. That was insightful in illustrating the difference between sample proportions and binomial theorem. Hopefully you liked the video. If you did, please, like the video, subscribe to the channel, and tell your friends. Thank you very much. See you at the next one.